is Janet and Rabia.
Welcome to Everest Physics Academy.
Before we start, we'd like to recommend our Everest Physics books for high school,
where you can find more explanations and solve applications and problems.
In this solved exercise, we are going to calculate the initial mechanical energy of the pendulum-Earth system. Calculate the maximum angle described by the pendulum. Determine the differential equation that governs the variation of the angular abscissa theta. Calculate the values of the natural angular frequency omega 0, the natural period t0, and the initial phase angle phi. Compare the period of energy with the natural period t0 of the oscillation. Calculate the average power furnished to the damped pendulum between time 0 and time 2t. Draw the curves of the amplitude theta m versus the angular frequency omega a of the exciter after increasing the damping.
A simple pendulum consists of a particle of mass 100 grams fixed at the free end of a massless rod OA of length 0.45 meters. This pendulum may oscillate in the vertical plane about a horizontal axis delta passing through the upper end O of the rod. The pendulum is initially at rest in its equilibrium position A0. At time 0, the particle is launched horizontally in the positive direction with a velocity of magnitude 0.3 meters per second. The horizontal plane passing through A0 is taken as the reference level for gravitational potential energy. Take the gravitational acceleration as 10 meters per second squared. For small angles expressed in radians, cosine theta can be replaced by 1 minus theta squared over 2, and sine theta can be replaced by theta. Part A. In this part, we neglect the forces of friction. Part 1A. Show that the mechanical energy of the system pendulum-Earth at time 0 is 4.5 millijoules. The mechanical energy at time 0 is equal to the kinetic energy at time 0 plus the gravitational potential energy at time 0. But at time 0, the object is at the reference level of gravitational potential energy. Then GPE at time 0 is equal to 0. Therefore, we still have the kinetic energy, whose expression is 1/2 mv0 squared. The mass of the particle is 100 grams. It is equal to 0.1 kilograms. The speed is 0.3 meters per second. Therefore, the initial mechanical energy is equal to 4.5 times 10 to the power minus 3 joules, which is equal to 4.5 millijoules.
Part 1b. Determine the expression of the mechanical energy of the system pendulum-Earth in terms of mv, Lg, and theta. The mechanical energy is given by the kinetic energy plus the gravitational potential energy, which is equal to 1/2 mv squared plus mgz, where z is the altitude of the particle relative to the reference level for the gravitational potential energy. Look at the figure. Z is equal to BA0, which is equal to OA0 minus OB. OA0 is equal to L. And using the right angle triangle OBA, cosine theta is equal to the adjacent OB over the hypotenuse OA. So OB is equal to L cosine theta. Then Z is equal to L into 1 minus cosine theta. Now replace Z by L into 1 minus cosine theta in the expression of ME. So ME becomes 1/2 mv squared plus mgl into 1 minus cosine theta. Part 1c. Deduce the maximum angle theta m described by the pendulum. Since their friction is negligible, or the sum of the work done by the non-conservative forces is 0, so the mechanical energy is conserved. So the mechanical energy at time 0 is equal to the mechanical energy when theta is equal to theta m, and me when theta is equal to theta m is equal to Ke plus GPE when theta equal theta m, and the kinetic energy when theta is equal to theta m is equal to 0. So me when theta equal theta m equal mgl into 1 minus cosine theta m. Now replace each physical quantity by its value. Me0 is equal to 4.5 times 10 to the power minus 3 joules, proved in the previous slide. M is equal to 0.1 kilograms. G is equal to 10 meters per second squared, and L is equal to 0.45 meters. Therefore, theta m is equal to 0.14 radians, which is equal to 8 degrees.
Let's move to part 2a. Derive the differential equation that governs the variation of theta, knowing that V is equal to L d theta by dt. So this is the expression of the mechanical energy obtained in the previous slide. We have V is equal to L d theta by dt, which is equal to L theta prime. Then replace V squared in the expression of the mechanical energy by L squared theta prime squared and rearrange. We will get this equation. But what is ml squared? ml squared is equal to the moment of inertia of the particle about the axis delta. Then we will replace ml squared in this equation by I. We get this equation. Now, friction is neglected. Therefore, the mechanical energy is conserved, or we can say that some of the works done by the non-conservative forces is equal to zero, then the mechanical energy is conserved. If the mechanical energy is conserved, then its time derivative is equal to zero. So let's differentiate this expression with respect to time. So the left side, dme by dt is equal to 0. Let's start with 1/2 I theta prime squared. 1/2 I is a constant multiplied by the variable theta prime squared. So the derivative of this term is equal to the constant 1/2 I multiplied by the derivative of the variable, which is equal to 2 theta prime theta double prime. MGL is constant, therefore its derivative with respect to time is equal to 0. Similarly, minus mgl is constant, then the derivative of the expression minus mgl cosine theta is equal to minus mgl times the derivative of cosine theta, which is equal to minus theta prime sine theta. 1/2 times 2 is equal to 1. We get this equation. The pendulum oscillates with small angles. Then we can replace sine theta in this equation by theta. Also, we will take theta prime as a common factor. We get this equation. This equation has two solutions. The first solution is theta prime is equal to 0, but this solution is rejected because if theta prime is equal to 0, then we have no motion, and this is not the case. Then the acceptable solution is this one. I theta double prime plus mgl theta is equal to 0. Divide this equation by I, which is equal to ml squared. We get this equation. The m's cancel out, L and L cancel out. This is going to be theta double prime plus G over L into theta is equal to 0. This is the differential equation that governs the variation of theta.
2b. Deduce the expression of the natural or the proper angular frequency omega 0 and the natural period t0 in terms of L and G. Using the obtained differential equation, this equation is of the form theta double prime plus omega 0 squared theta equals 0. So comparing the last two equations gives omega 0 squared equal G over L. So omega 0 is equal to the square root of G over L. T0 is given by 2 pi over omega 0. Replace omega 0 by the square root of G over L. Therefore, T0 becomes 2 pi the square root of L over G. 2c. Calculate the values of T0 and omega 0. Omega 0 is given by the square root of G over L. Now replace G by 10 meters per second squared and replace L by 0.45 meters. Therefore, omega 0 is equal to 4.71 radians per second. T0 is equal to 2 pi over omega 0. Replace omega 0 by 4.71, then T0 is equal to 1.33 seconds.
Let's move to part 3. The time equation of the motion of the pendulum is of the form theta equals theta m sine omega 0 t plus phi. Determine the value of the constant phi. You know that the value of phi is determined from the initial conditions. In the beginning of the question, we said that at time 0, the particle is in the equilibrium position. Therefore, theta 0 is equal to 0. Also, we said that the particle is launched in the positive direction, then theta 0 prime is positive. Now, we will replace t by 0 and theta 0 and theta by 0 in the expression of theta. This is going to be 0 is equal to theta m sine phi. We know that theta m is different from 0. Therefore, sine phi is equal to 0. If sine phi is equal to 0, then phi is equal to 0, or phi is equal to pi minus 0, which is equal to pi radians. One of these two values is the correct value. Let's move to the expression of the angular velocity of the pendulum. So we will differentiate this expression with respect to time. The derivative of theta with respect to time is equal to the constant theta m multiplied by the derivative of sine omega 0 t plus phi. The derivative of sine omega 0 t plus phi is equal to omega 0 cosine omega 0 t plus phi. Now, we want to replace t in this expression by 0 and theta prime by theta 0 prime. We get this equation. We know that omega 0 theta m is a positive quantity. Also, theta 0 prime is a positive quantity. It is given in the beginning of the question. Therefore, cosine phi is positive. If cosine phi is positive, then we will choose the angle phi, which is equal to 0, because cosine 0 is equal to plus 1, while cosine pi is equal to minus 1. If cosine phi is positive, then 0 is the chosen angle.
Focus, please. This is important.
4. The adjacent figure shows three curves which represent the kinetic energy Ke, the gravitational potential energy GPE, and the mechanical energy ME of the system Pendulum-Earth. 4a. Identify each one of the curves A, B, and C in the figure. We know that the mechanical energy is conserved. Look at the figure. Curve C is parallel to the time axis, so curve C represents the mechanical energy. At time 0, the particle is on the reference level, so at time 0 the gravitational potential energy is equal to 0. Look at the figure. The energy corresponding to curve A at time 0 is equal to 0, so curve A represents the gravitational potential energy. Also, we know that at time 0 the speed of the particle is not equal to 0, so the kinetic energy at time 0 is not equal to 0. Look at the figure again. The energy corresponding to curve B is not equal to 0 at time 0, so curve B represents the kinetic energy.
Let's move to part 4b. Pick up from the figure the value of the period TE of the variation of the energy. Look at the figure. Consider curve A. At time 0, this energy is 0. Then it increases to become maximum, and then it decreases to become 0 again at time 0.67 seconds. Then this curve repeats itself identically each 0.67 seconds. Similarly, for curve B, at time 0, its energy is maximum, and then it decreases to 0, and then it becomes again maximum at time of 0.67 seconds. Therefore, the period of the energy is equal to 0.67 seconds. Part 4c, deduce the relation between TE, which is the period of the energy, and T0, which is the oscillation period. In a previous slide, we calculated the value of the oscillation period. It is 1.33 seconds, but the period of the energy is equal to 0.67 seconds. Therefore, the oscillation period, or the natural period of oscillation, is equal to 2 times the period of the energy.
B. In reality, the forces of friction are not negligible. The angular abscissa theta of the pendulum as a function of time is represented by the graph of the adjacent figure. 1. Refer to the graph in order to indicate the type of oscillations performed by the pendulum. Look at the figure. The amplitude decreases with time, so the type of oscillation is called the free damped oscillations. 1b. Determine the duration t of one oscillation. This duration is called the zero period of the oscillation, and then compare t and t0. Look at the figure. The pendulum performs 1, 2, 3 oscillations during a time of 4.1 seconds. So the time needed to complete one oscillation is equal to 4.1 over 3, which is equal to 1.37 seconds. T0 is calculated before and is equal to 1.33 seconds. So T is slightly greater than T0.
Let's move to part 2. Given that the kinetic energy of the pendulum at the instant 2t is 2.74 millijoules, determine the average power furnished to the pendulum in order to compensate for the loss in energy between 0 and 2t. The average power is given by this expression, the furnished energy divided by the time. The furnished energy is equal to the absolute value of the variation in the mechanical energy, because in order to compensate for the loss in energy, we must provide the system with an amount of energy which is equal to the lost energy. Delta ME is equal to ME final, which is the mechanical energy at 2t, minus ME initial, which is ME0. Let's start with ME at time 2t. ME at time 2t is equal to the kinetic energy at this time plus the gravitational potential energy at this time. Look at the figure. This is time 0, this is time 1t, and this is time 2t. At time 2t, the particle is at the equilibrium position because theta is equal to 0. This means that the particle is at the reference level for the gravitational potential energy, which means that gravitational potential energy is equal to 0 in this position. Therefore, we still have only the kinetic energy, which is equal to 2.74 millijoules. It becomes 2.74 times 10 to the power minus 3 joules. Therefore, the mechanical energy at 2t is equal to 2.74 times 10 to the power minus 3 joules. The initial mechanical energy is obtained in a previous slide. It is equal to 4.5 times 10 to the power minus 3 joules. Now we are ready to calculate the average power. Then the mechanical energy at time 2t is equal to 2.74 times 10 power minus 3 joules. The initial mechanical energy is 4.5 times 10 to the power minus 3 joules. And capital T is equal to 1.37 seconds. It is obtained in the previous slide. Therefore, the average power is equal to 0.64 times 10 to the power minus 3 watts.
Part C. The pendulum undergoes periodic excitations of adjustable angular frequency omega e. This means that the pendulum is coupled to an exciter having an angular frequency omega e. We record for each value of omega e the value of the oscillation amplitude theta m, and we trace the graph of theta m versus omega e as shown on the adjacent figure. 1a. Name the phenomenon that takes place in the graph. Look at the figure. For a certain value of omega e, theta m is maximum, so in this case we have an amplitude resonance. 1b. Give the value of the angular frequency omega e at which the oscillation amplitude is maximum. We know that when we have an amplitude resonance, the angular frequency omega e of the exciter is approximately equal to the angular frequency of the resonator, or the natural angular frequency of the resonator. So omega e is equal to 4.71 radians per second.
Let's move to part 2. An appropriate system increases slightly the forces of friction. Redraw the adjacent figure and roughly draw the shape of the curve giving the oscillation amplitude theta m of the pendulum as a function of the angular frequency omega e. We know that when the value of the friction increases slightly, this means that the damping increases. And when the damping increases, the amplitude in case of resonance, which is called the resonance amplitude, decreases. The curve broadens, which means that the peak gets broader. The peak of the curve of theta m versus omega e moves to the left. Look at the red curve. It has a resonant amplitude which is less than the original one, and the curve is broader than the original one, and its peak moves to the left because the phenomenon of amplitude resonance takes place at an angular frequency omega which is less than the original value of omega.
Thank you for watching. If you like this video,
subscribe to the channel, hit the like button and share.